What's going on, Algebros? It's Mr. C here, and in this video we're going to derive the cube root function, another function from the library of functions, and it's called the cube root function because of how we operate on the inputs. In particular, any value of x that we choose, we're going to have to apply the cube root of it in order to figure out the y value. So let's go ahead and start there. You'll notice that the x values I've picked not only include positive values but also negative values this time, which is something that's immediately different from the square root function. Recall that you can take the odd root of a negative number, and that's purely based on the fact that at some point, you could break it up into like the cube root of -1 times the cube root of the positive version of the number, and -1 does have a cube root that's equal to -1. Anyway, if we go ahead and work with these x values, the corresponding y value for -8 is found by doing the cube root of -8, which is equal to -2. And that gives us our first point to plot. -8, so go left from the origin to -8 and go down to, is our first point. Cube root of -1, as I already mentioned, the cube root of -1 does exist, and it's -1. So -1 is another point. Cube root of 0. Cube root of 0 is 0. So this is another graph that goes to the origin. Cube root of 1 is 1. The graph also goes through 1, 1. And then the cube root of +8 is going to be +2. So 8, 2 would be our final point to be plotting just based on this table of values. Of course, you could choose more and more x values to get a more accurate graph. This is probably good enough to get an idea of how this graph goes. Let's start connecting the points. I'll start at -8, -2, go through -1, 1. It's going to snake its way through the origin, and then just kind of hook off to go through 8, 2, and I'm going to extend that end of the graph and also extend the end of the graph down at -8, -2. We'll extend out to the left and put a little arrowhead. So that is the sketch of the graph of the cube root function. Now for the details, this graph is fully connected, and one end of the graph continues to the right indefinitely while increasing. The other end of the graph continues to the left indefinitely while decreasing, and is fully connected. I think I already mentioned that. And the only way we could get this graph to behave in this way is if we're using all the x values from the x-axis. Another way is to just look at the rule of the function. There's no spot to divide by 0, and as mentioned, you can take the cube root of a negative number, so we don't really have to worry about negative inputs. Actually, we have some evidence from the table that negative inputs give us some real number outputs versus imaginary. So either way you slice it, the domain is going to be all real numbers. As for the range, you can look at the two ends of the graph again. Or you can kind of break this graph up into two pieces. If you look at the piece in quadrant 1, this end of the graph slowly increases to positive infinity, which means that any y value from the positive part of the y-axis is going to be serving as a y-coordinate. We're obviously using y equals 0, and this section of the graph is using all the negative values from the y-axis, because this part of the graph shows us that it goes down to negative infinity, just kind of at a slower rate. In other words, we're using all the values from the y-axis as a y-coordinate at some point on the graph. All right. So in other words, every y-coordinate from this graph is utilizing something from the y-axis. All right. So the range is all real numbers. For even or odd, what I want to point out is that this graph has origin symmetry. If you were to take the piece that's in quadrant 1, mirror it across the y-axis and then mirror it across the x-axis, it should, all things considered, line up with the piece that's in quadrant 3. And vice versa. That is, you could reflect the piece in quadrant 3 across the y-axis, then across the x-axis, and it should line up with the piece that's in quadrant 1. Alright, so because this graph has origin symmetry, this would be a function that is odd. All odd functions have origin symmetry. Orange, you glad you know that now? Alright, just kidding. From an analytic perspective, if we compare the three expressions, f of x, f of negative x, and negative f of x, we get some good information from here. Of course, f of x is the cube root of x. It's nothing to really do with that. F of negative x, we'd have to do the cube root of negative x, which you could break that up as the cube root of negative 1 times the cube root of x, and the cube root of negative 1, as we see in the table, is negative 1. So in other words, the fully simplified form of f of negative x is negative cube root of x. Now, negative f of x requires that we take negative 1 and multiply it to the original function expression. So we'd have to take negative 1 and multiply it by the cube root of x, thereby giving us negative cube root of x. And you can see that f of negative x's expression is equal to negative f of x's expression. And for that reason, this would be an odd function. All right, so that's the analytic way of showing that. As for increasing, decreasing, and so on, if you start at the left end of the graph and trace your finger going from left to right, you would see that your finger starts out increasing on your page, continues to increase maybe at a faster rate, and then still increasing, but now at kind of a slower rate. Regardless, this graph is always increasing. All right, and the x values that make this happen would actually be all of them from the x-axis. So the increasing interval would be negative infinity to positive infinity, which means that this graph is not decreasing. So we'll say NA for that. Okay, no parts of this graph are going down from left to right. They're all going up from left to right. And that's how we derive the library function, the cube root function.